Hello everyone. This is Saidul Hassan from Information Technology University in Pakistan. I'll be presenting my work entitled Measuring Scientific Knowledge Flows by Deploying Citation Context Analysis using Machine Learning Approach on PLoS 1 Full Text Data. In this research, I had my peers Anam Akram, Awais Asghar, and Professor Dr. Naif Radi Al-Juhani from King Abdulaziz University, Saudi Arabia. First of all, I would like to give the motivation of my work regarding knowledge flows. It came from the concept proposed by Hegel, and he narrates that knowledge flows which occur in any social fluid environment where learning and collaboration can take place are quickly becoming one of the most crucial sources of value creation. So I personally believe that measuring knowledge flows is extremely important for understanding the scientific research landscape and the dynamics associated to it. Few concepts that are that also derive the motivation for understanding the knowledge flows are that understanding a research landscape requires understanding the dynamics of relevant research knowledge flows. For example, knowledge inflows and knowledge outflows. Similarly, knowledge outflow shows international research influence of scientific research, and if one country serves as a source of knowledge for other countries, this can help to produce a positive environment for marketing its commercial technology and can contribute to positive international dependencies. Previously, scientists have been pursuing to measure knowledge flows from the community of scientometrics and informatics. For instance, Zhu argued that citation between scientific article may imply a knowledge flow from the authors of the article being cited to the authors of the articles that cited. More comprehensively, measure flows have been measured by understanding the knowledge between two countries, for instance A and B, by considering citation from papers authored by the researchers in one country to those of papers authored by the researchers in another country, for instance. The data of the citation exchange among the authors from different countries have been visualized also, and we find quite a fancy geographical distribution of maps as one you can see on your slide. For instance, in this graph, the field of energy, the data published in the field of energy between 1996 to 2009, in which one of the authors from the United States has been considered, and then the publications being, and then the citations being made to those publications can show the large volume of knowledge outflow from the US to China, Japan, and many European countries, for instance. So I'm going to put my problem statement here. We argue that since knowledge flows have been heavily used using simple citation counts, so we argue that not all citations are equally important. Therefore, in contrast to existing techniques that utilize absolute citation counts to quantify knowledge flows among different entities, our model employs citation context analysis technique using machine learning approach to distinguish between important and non-important citations. For this very reason, we found that some state-of-the-art already exists that actually classify citation into an important one and a non-important one. We present a few of them, the more recent and state-of-the-art. For instance, Zhu's work published in JSIST in 2015, they present a model to identify citations that have a central academic influence on the citing paper. They use count-based, similarity-based, some contextual and position-based features for that, and then deploy a supervised machine learning approach. Another state-of-the-art by Valenzuela in 2015, published in AAAI, classifies the citation into 4 categories, for instance. They group it into incidental related work, incidental comparative work, and important class has two categories of using the work or extending the work. So for instance, if the citation is used just to show the background work or some related work, then it would be non-important for them. And if the citation has been used to extend a work or and actually utilizes a model from an existing work, then it would be an important work. They report on a certain data set, they report their area under the curve precision recall about 0.8%, which is quite encouraging for this kind of work using SPM and random forest models. So in our proposed solution, we choose some of the existing feature in some of the state-of-the-art that we found, and then propose some additional features for this task of classifying a citation into important and non-important one. And then for this very reason, we actually choose 8 from the previous work, from the work of Valenzuela and Zhu, and we actually then deploy 6 new features. I will explain in the details. And then finally, our deployed classification model using random forest, it actually improves the existing state-of-the-art of Valenzuela by 10%. And at the end, we also deploy a case study using the PLoS 1 full text publication in the field of computer and information sciences to see the effectiveness of this method that we actually propose. So we propose actually 2 kind of contribution in this paper. One is the algorithmic improvement of existing state-of-the-art in distinguishing important and non-important citations, and the other one is this case study that actually helps us to understand the knowledge flows across different regions using important and non-important citations. So our approach for identifying an important versus non-important citation contains following 3 steps. So at first, we believe that a reference is important to a paper if it has been cited several times in the body of the citing paper. The second is the position of the citation would influence its importance. For instance, if a paper is cited in somewhere, for instance, introduction versus a method section, then these 2 positions carry different weight. And third thing is the citation around, the text around the citation in the body of the citing paper. We believe it's important since it would indicate the reason for the citation. So when you cite a paper and then the text around that citation would also reflect the reason for that citation. So as I mentioned that we had 14 features. 8 of them actually were classified as context-based feature, 4 of them were queue-based feature, and 2 of them were textual features, and I'll explain the details of them. For the context-based feature, we started off with some very simple features. For instance, total number of citations received by a reference. F2 goes as number of citations from a current paper to cited paper. F3 is citations in introduction section, citations in the literature review section, for instance, citation in method, experimental or discussion, or conclusion section. So these were actually the context-based citation features. For the keyword-based features were very important. So we had F9, feature F9 and F8, which were related to the related work citations and comparative work citations. So we found actually 49 different keywords. So these keywords were actually identified, manually identified by reading through the papers, that these keywords are usually found when the citations are not very important. And then another set of 80 keywords which we identified when a citation is important in terms of using the existing work or extending the existing work. So eventually we merged feature F9 and F10 together as for the non-important citations, and F11 and F12 for distinguishing an important citation. So F9 and F10 were merged, and similarly F11 and F12 were also merged for the model, for training the model. The list of these keywords can be found on paper. For the last textual features, We had a similarity between the abstract of cited paper and the text of citing paper with cosine similarity measure using DF-IDF approach. We end up using this very simple approach. Probably we will enhance the similarity measure in the subsequent research. And the last feature was with the author overlap. So we set it to true if the citing and cited paper have any common co-author. So using these 14 features, we trained our database, and for the training, we actually used the same dataset as used by the Valenzina in his paper published in AAAI. And there you can see that they start off with 4 different classes of citations: related work comparison, using the work or extending the work, and then they end up combining related work and comparison into one class as an incidental or non-important, or using the work or extending the work into one important class. We chose the same dataset for training our model because this dataset has been manually annotated, so one can see the accuracy, learning accuracy while training the data. And this dataset actually taken from the Association for Computational Linguistics anthology. About more than 20,000 papers were there, and then among them 465 citations were randomly selected and annotated by this group, and we chose the same dataset to train our model. For the test data, here comes our case study. We chose a PLoS 1 full text database for this, and in the subject area of computer and information sciences, we chose the time window from January 1st, 2014 to September 1st, 2015. And the total number of publications, including articles, reviews, and anything that actually was in that data set during that time window was considered, which were 4,138 papers. And then we also fetched the unique references that were cited in those publications. There were actually more than 30,000 references, unique references. Some of the references can be overlap, in these 4,000 publications. But for the unique references, we had about 30,000 unique references. But among them, we found only 21,804 references in Scopus database, because for the further information for these references, for instance, the affiliation from where these authors are, we had to use a Scopus API to fetch that information. So we use Scopus API for this information. For instance, the abstract of the references and the author's affiliation to address some of the questions for our case study. This is the overall flow chart of the deployed approach that I will quickly go through. We had, for instance, a PLoS 1 corpus, then we downloaded the publication in XML, and then the XML parser was written. Then these from XML to text files were generated. Furthermore, we had this parsite toolkit to convert to get certain chunks of text that were needed for further processing. We fetched citation text and the location, and then the tokenization was done using Python. Further, we performed, punctuation, removal of the punctuation, HTML tags, and stop word, which are the standard lemmatization or the pre-processing techniques. We also had POS tagger and that were used to extract synonyms using WordNet to enrich the vocabulary for matching the abstract with the keywords around the citation, for instance. And eventually, with all these processing, we had 14 features extracted, and then we did the standard feature normalization before we give our data for training to scikit-learn, and eventually the results were displayed. Let me show you the first result, as you guys can see, related to knowledge flow from the United States. So this shows the distribution of references published by the authors across the countries, cited in the papers published by the authors from the United States. So this shows that when the authors of United States, they write a paper, what are the papers they cite in their work, for instance. So on your left you see all references, and on your right you would see important references. For instance, if I see the first graph on your left hand, all references, it shows that United States utilizes about 53% of the total references in their work within itself, and then they use United Kingdom's work with about 7%, and China's scientific literature being cited in the US publication about 5%, and so forth, you see. For the important references, so these are now the important citations that actually are influential, and then they actually are being used for extending the work, or being used to utilize the work. And for that, the United States utilizes 74% of its own knowledge resources. So there, the dependencies of United States on its own knowledge, on its own important knowledge by our definition, improves significantly, and its dependency on Chinese, for instance, knowledge decreases to 1.6%. Whereas Germany, Sweden, Canada, Netherlands, we can see, are pretty much there next to United States. So this is we find this insight very interesting, and then we can go through for certain more use cases and see how different countries reflect when it comes to cite their own knowledge resources, or borrow the knowledge from other countries in terms of citations, and more importantly in terms of those citations which are academically influenced. Now I show you the use case of United Kingdom, for instance. Here we see that for all references, United States position stays there with 27% of the references that comes from the United States, while from the United Kingdom itself, about 26% of the references come. Germany, Australia, and China are then the following countries. So when it comes to important references, United Kingdom heavily depends upon its own knowledge resources. Of the total important references cited by the work of United Kingdom, 47% comes from the United Kingdom itself, followed by United States, Netherlands, Germany, and China with about 2%. We also can see the position of Canada in terms of this knowledge exchange, both for in terms of citing all references or citing important references. Canada heavily depends upon United States, followed by Canada itself, and then United Kingdom or Netherlands in cases of all references and important references. Last but not the least, I would also show the use case of China. So Chinese interaction in terms of citing scientific literature looks different compared to other countries, and it looks similar to United States, for instance. Among all the references that are being cited by the Chinese authors in their publication, 39% actually comes from the China itself, followed by the United States and United Kingdom. And when it comes to the important references, China again heavily depends upon its own knowledge resources. So this is a pattern, and followed by United States and United Kingdom. So this is a pattern that we found in United States in terms of depending upon its own knowledge resources when it comes to all references or the most significant relevant knowledge resources, for instance. I found it interesting. We also wanted to show that of the total um, references being made from a given country, what proportion is actually the important one? Because in some cases, some countries may not be publishing a lot, so they end up offering very few citations to other countries. And we found that so in this analysis, what we did, we normalized the total references with the important references only, and we found, and the list goes as follows, that we found Austria, Sweden, Brazil, Netherlands, despite the fact they are publishing relatively less compared to giants like United Kingdom, Germany, or China, they appear to be at the top. China somehow make at the end of this list with only 4% of the total references are actually the important ones. So of 4,286 references, 176 are important one in this data set. We also wanted to visualize some knowledge flow networks. So this is the one, for instance, on your screen, is using all references across the countries. We see heavy knowledge exchange between China and United States. So interpret this map would be more darker you are in the circle, more influential country you become, and the arrow actually directs the citation from one country to another country, citations being made from one country to another country. And the United States, we see a lot of exchange between USA and China, USA and United Kingdom, similarly Germany, and USA with Netherlands and Canada as well. A similar graph was generated using only important references. For that very case, the position of China actually changes, and we see that United Kingdom now seems to be overtaken by the China in this very data set at least, and also Germany and Australia look more appear to be more influential in this network, and US overall is very influential overall when it comes to the important references. And I will just put these two graphs next to each other here, and then we can clearly see on your left hand side when all references were being used, and on your right hand side when only important references were chosen to draw this network. We find that the significance of the United States is even more visible when it comes to important references. China loses its place when it comes to important references compared to all references, for instance. So I would then put my concluding remarks before due to the shortage of time. I would say that our results have shown that despite an exponential increase in publication output by the Chinese scientific community, the most important global knowledge flows that are consumed by the international scientific community are still exhibited by the United States, followed by United Kingdom and Germany in our dataset. We have also highlighted that in contrast to many other nations analyzed in our dataset, the dependence of China on the knowledge produced by its own scientific community is even more significant when it comes to the most important knowledge flows produced by the China. And I think this may have many implications to the citing behavior of different communities, and I think this is also an interesting research questions for the future research. I would extend my concluding remarks that in future we also plan to improve our machine learning model by including more features such as citation sentiments like negative, positive, or neutral. We believe that this would significantly improve the accuracy of our model. Last but not the least, our proposed model is significant contribution, and these could be a few of the contributions that I would like to highlight. That to understand the dynamics of the relevant knowledge flows across the nations, for the algorithmic techniques that can detect and follow the emerging research topics, and to quantitatively measure the impact of publications in increasingly growing scholarly big data. This pretty much concludes my presentation. I'm thankful to the organizing committee who allowed me to present my work using this video link. I've been attending ISSI for last many years now, but due to some delays in the visa availability, unfortunately I could not make it to ISSI this year, and I hope to see you guys and join you in coming years. And for any questions, I'm happy to receive your feedback on my email address, which is saeed-ul-hassan@itu.edu.pk. And I would also encourage you guys to visit our lab's website, which is the only scientometric lab in Pakistan. And the website URL goes as www.slab.itu.edu.pk. Thank you so much for your time. Thank you.